All right, so today let's talk about kinetic theory, the kinetic theory of gases. So why develop this kinetic model? All right, so far we've talked about kind of the macroscopic understanding of kind of what's going on with thermal physics, meaning we're kind of looking at the big picture of what pressure and temperature is. Um, Now, a kinetic model is taking more of a microscopic approach, see what's going on kind of in detail with the molecular motion of the gas. All right. So this is what the kinetic theory of gases is. So we're assuming that a gas is made up of molecules that are continuously in random motion. So this allows us to better understand what pressure means microscopically rather than macroscopically, because macroscopically we know pressure is force over area, but why is it force over area? So the reason for that is, let's assume we're looking at some sort of a container of gas. So here's a wall of that container depicted here. When we have a molecule of gas and it hits that container wall, well, that's going to change the velocity of the molecule, right? And we know that the only way it can change its velocity, change its momentum, is having a force exerted on it, an impulsive force, right? Because we have a change of momentum here, so that's impulse. Um, so, and we also know that there's an action-reaction pair, right? So if there's a force exerted on the gas molecule, then there's an equal and opposite force exerted on the wall. So here, whenever a molecule of gas hits the container wall, it exerts a force, right? Well, if we have more molecules, more gas molecules hitting and bouncing off the container wall, then we'll have a an overall net force acting on the container. And since the container has some sort of surface area, we have an average force over surface area being pressure. So this is why pressure exists. Now I do want to emphasize here the second statement. I already talked about the first here. But this pressure doesn't only exist on the container surface, it exists in the system itself, meaning the system being the gas. Because these molecules are also interacting with each other and doing the same thing on each other. So the pressure exists in everything here. All right, so we could derive a formula. I'm not going to, but we'll take for granted here that we can have this relationship that pressure times volume of a gas is equal to 1/3 mv squared average. Ooh, okay, let's see what's going on there. So we've got a value of 1/3, and we multiply that by n, which is the number of molecules in a container, multiplied by m is the mass of one molecule. So basically what we're doing there is that n times m is effectively the mass of the gas. And then we have v squared going on. So just be careful. So this bar up top is meaning average. And the bar is on top of the quantity v squared, not on top of the quantity just v. So this is the average of the velocity squared, not the square of average velocity. Those are mathematically very different. If you took statistics, maybe you have some insight on that. But they're not the same thing, so just be careful. And this v is here. This is the average molecular speed squared. All right. So we have this formula. If you can kind of look at it, it looks pretty familiar, right? I mentioned in the last video about the ideal gas law that the quantity PV, that's related to work. And again, we're going to get more into this later this unit, but this is an energy term. If you're looking here, well, this is also an energy term. In fact, it looks pretty somewhat similar to kinetic energy, right? We've got, well, kinetic energy we're familiar as being 1/2. We have a third here, but we've got a mass quantity and a v squared quantity. So this does have units of energy. But we could do a little bit more math. I'm not going to get to an expression for average kinetic energy, right? So if we're computing average kinetic energy, so here's kinetic energy, again, the bar here means average, that's going to be 1/2 I'm assuming that our gas is all the same molecule, so M is the same for every atom, times V squared, the average of that quantity. We can actually relate this to temperature, right? So basically, we'd relate this to the ideal gas law and rewrite it in terms of temperature. And we end up with 3/2 K times T, where that K is the Boltzmann constant again, and T is the temperature of the gas. So you might be thinking, where are all these 3 numbers coming from, right? We never really dealt with things having a 3 in it before in physics class. Kind of a long story short, it has to do with the degrees of freedom that gas molecules have. We'll just chop it up to they're always moving in three spatial dimensions, right? We can't assume that they're moving in just 1D like we did for a lot of introductory physics. So what's interesting here is that now we've developed kind of a microscopic definition of temperature. So our temperature is going to be related to the average kinetic energy of the molecules. So the faster that the molecules of a gas are moving, the higher the temperature is going to be, because the higher the average kinetic energy, well, the only thing that can change on the right-hand side of this equation is temperature, right? Because the Boltzmann constant is a constant, and so is 3/2. So kinetic energy and temperature are directly proportional to each other for a gas. We can also determine something called the root mean squared speed. All right, so RMS speed is another way of saying this, right? So if we take that equation we have and rearrange things, we end up with this formula here, which is kind of an average speed of the molecules of a gas in terms of temperature. This is pretty interesting to kind of gain information about this. Though I do want to state, right, all the molecules in our gas are not moving at the same speed, right? They're bouncing off each other. They're exerting forces on each other. It's just that, over time, a lot of the molecules are going to have an average speed, and there's still going to be some that are not the average. I'm really explaining that, not the best. I go into a little bit more later with some graphs, so don't you worry. But let's look at an example here. So let's suppose we wanted to calculate the kinetic energy and speed of a gas molecule. So let's find the average kinetic energy for a gas molecule that's at 20 degrees Celsius, so that's room temperature. And then let's also find the RMS speed for a nitrogen molecule at this temperature. So writing down what we know temperature, so let's convert that to Kelvin or SI units. So that becomes 293 Kelvin. And I also jotted down the Boltzmann constant here since I'm thinking we're going to need to use that. So the average kinetic energy we had in our formula is 3/2 kT. So we're plugging in Boltzmann constant, and the temperature in Kelvin gives us 6.07 times 10 to the negative 21 joules. So a very small amount of energy, but that seems reasonable because we're dealing with one gas molecule that's just moving around in regular temperature. So that's not going to have too much energy. Okay, so now we want to find the RMS speed for a nitrogen molecule. All right, so our RMS speed is going to be the square root of 3 kT over m. All right, so now what we have to be careful with here is that the m we're dealing with, this mass, is the mass of a nitrogen molecule. So we need to compute that, right? We're not given that information. So what I'm doing here is basically using the periodic table to our advantage. So very similar to what we've done in what you've done in chemistry class, right? So in the numerator here, I've got 2 because we have two atoms making up this molecule, because it's N2, and I multiply it by the molar mass of one atom of nitrogen and divide by Avogadro's number to make our units work out to give us just the mass. So then the mass of one molecule of N2 is 4.56 times 10 to the negative 26 kilograms. So plugging in all these numbers and being very careful with our calculator, we end up with an RMS speed of 511 meters per second, which is a very typical number. So kind of in the future, just kind of keep that in mind. So it's a very fast number, right? 500 meters per second is a fast speed, but we're dealing with molecules of gas, and those move quickly. So RMS speed is not going to be, so basically the average molecular speed of a gas is not just one value. Well, I guess the average is, but we have these distributions to help us kind of describe the speed of the molecules in a gas. Right, and the reason why they're all not moving at the same speed is because the motion of the gas is random. So what we have is what are these called these Boltzmann, Maxwell-Boltzmann distributions. They're pretty interesting to look at. But these graphs here are showing the probability of a certain gas having a certain speed. So for example, you can see here that the purple graph being xenon. Is that xenon? I'm going to go with that. But a very heavy molecule. Since the molecules are so heavy, their speed is pretty confined. We're going to find the molecules being between 0 and 500 meters per second. Whereas we're looking at the dark blue line, which is helium, a very light molecule, or atom. Why am I saying molecules? Atoms here. Because they're so light, they can very easily change their momentum. So their distribution is much wider. It can find a much wider range of velocities for the gas. So I will state here, I have seen these distributions on the AP exam before. So just kind of want to mention that now. Now I do want to mention, so these distributions, they're not normal, right? Like mathematically normal. These have a longer tail, right? Because you're not going to have molecules have a speed below 0, but there is a finite possibility that you're going to have molecules with a very fast speed. Not many of them, but it's available. So the consequences of this is that the RMS speed is going to be higher on this curve than the most likely speed for a molecule. So that's a pretty interesting consequence. Now, temperature is also going to affect this type of distribution, right? So because we saw that the kinetic energy of a gas is directly proportional to temperature, the higher a temperature is, the faster the molecules are going to be moving. So because of this, what's going to happen is as if we have some sort of a gas, as the temperature increases, this curve is basically going to start flattening and widening out. Because there's going to be more molecules able to get higher speeds, but they can also have smaller speeds as well. So so these curves are going to flatten and spread. Again, I've seen these on the AP exam before too. So it's pretty interesting, the information and kind of consequences mathematically of what's going on. But I digress. You can find more information about this in your textbook if you find it pretty interesting.